Welcome, everybody. We'll get started in just a minute or two. We'll just give folks a moment just to join and get things set up. Welcome, everyone. I just want to give everyone just another moment or so to join, and then we'll get started. So hang on. All right, welcome, everybody. We're going to go ahead and get started. There's me. So I'm here to talk about on-call or not on-call using distributed tracing to improve reliability and performance. Before I get started, just a few housekeeping things. Just so everyone knows, we're recording today's session. We'll send out a link to the recording as part of the follow-up. So if there's someone you'd like to share it with, or you have to jump out early, you can take a look at that. And if you have any questions, use the Q&A bar at the bottom. I'll try and get those towards the end of the talk. And yeah, it's great to have participation from folks as well. So with that, just a few words about me. My name is Daniel Spoonhauer, or Spoons. I'm the CTO and a co-founder at Lightstep. Lightstep provides simple observability for deep systems, observability with distributed tracing at its core. I spent a lot of time not just thinking about distributed tracing, but also using it. Before I helped found Lightstep, I was an engineer at Google, where I worked on Google's infrastructure and as part of their cloud platform team. And I carried a pager for many years and thought a lot about performance, both for my own teams and for the other teams that I was supporting within the organization. More recently, I've also been working on another project. I'm one of the authors of Distributed Tracing in Practice, Instrumenting, Analyzing, and Debugging Microservices. I'll talk a bit more about that later. So to kind of set some context for today, why did I call this on-call or not on-call? I kind of think of these as two sets of use cases, right? So on one side, we have cases where we're on call. And you might think of this as an urgency thing, but really, I think it's actually kind of a different goal in a way, right? So when we're on call, usually we're thinking about restoring baseline performance, right? We've had a regression and we want to go back to the way things were back when everything was fine. And on the other side, we're trying to improve that baseline performance. We might be thinking about re-architecting part of our system, or maybe just doing some performance optimizations. But it's about improving that sort of status quo in a way. And when we think about performance and about on-call and not on-call in the age of DevOps, one of the things is that even if we divide them into two sets of use cases, they both might be being carried out by the same group of people. So it's helpful to have a common set of tools to handle both sets of requirements. And in fact, I might argue that it's more than helpful. It might actually be close to necessary, since when you're on call, you don't want to reach for a new tool, right? So if these are the same tools that we're using to improve baseline performance, that allows us to get an understanding and familiarity and build confidence in those tools when we move to a case when we're trying to restore that baseline performance. And like I said, not necessarily an urgency thing, but we definitely feel urgency when we're on call often. I also like to put performance in a business context. Maybe you all do this all the time, but just to give some explicit kind of context for this is performance is important partly because of the expectations that our customers have. They might have some expectations around the responsiveness of the application or around the speed with which transactions are processed. They might also be concerned about the correctness, not always, or maybe different kinds of correctness, but that can be something that's important to them. And if we don't meet those expectations, there can be some consequences of that, right? We can lose reputation. It can affect our brand in some way. We can lose revenue, right? If those transactions were important for our revenue. And if we've made those expectations with our customers explicit and through something like a service level agreement, then we might actually have to pay penalties if we fail to meet those expectations. Those are also kind of external costs in a way. The other kind of costs are more maybe internally. So of course, the application has to run somewhere, right? We have to use some computing resources, some storage, some network, some infrastructure to run it. So that has costs. And there's also a cost of operating the software, right? We need to pay engineers and they need to spend their time to do things like be on call to address situations that happen when production systems, and also think about how to optimize and to make sure that we're getting the most out of that infrastructure. And if we fail to do those things in the right way, well, we can miss our budgets in terms of our infrastructure spend, and we can also take a hit in terms of developer velocity, right? So developers, if they're spending time responding to pages, if they're spending time working on performance optimizations, that's time when they're not working on functional requirements, right there. And so we could take a hit in terms of developer velocity, and especially in the case of on-call. But I think even if you're just, always doing performance work and kind of grinding on that side of things, that can lead to burnout, right? And that can manifest itself in terms of morale or even things like turnover. I want to show this graph just to kind of make sure, I said performance and reliability, right? And in some ways they're not different because, reliability is really about what you promise your customers and your ability to deliver on that. And if you promise them performance, then you're not delivering on that reliability. I also put this graph in here because, you can see it's kind of, this is a latency graph over time, and you can sort of see it stepping up. And at some point it kind of hits this plateau at maybe not surprisingly or suspiciously at 30 seconds. And that's because there's a timeout, right? And what was slow performance became a failure, right? Often failure can just mean too slow. And so even when we're thinking about performance, that can still manifest itself in terms of a failure from a user perception. Okay, so how do we address that? Well, I think if we take actually both sets of use cases, they kind of come down to answering this one question: what caused that change? Because really it's thinking about what's changed in our systems that helps us understand how to fix them. And that change can be fast in the sense that it can be rapid, right? So it could be something like a new software release. It could be a configuration change. Infrastructure outages are often quite fast, right? So we could lose power, or there could be some other outage at our cloud provider. And then there's these sorts of nonlinear behaviors like this latency graph I was just showing, right? Where we have a more continuous performance characteristic that suddenly becomes discrete when it hits a particular threshold. Now, change can also be slow on the other hand, right? We can have changes that occur over weeks or even months, right? So we can have things like organic user growth or shifts in user behavior. We can also have things like resource leaks, right? Where we don't see them initially and we only really feel the consequences of them, again, hours or even days later. And in both sets, whether that change is fast or slow, we want to understand how the software was behaving before the change so that we can compare it to how it was behaving afterward. And I think, maybe it sounds simple to say it that way, but it can be really powerful because there's constantly things changing in distributed software systems, especially if you think about all the changes that are happening with your cloud provider, with your other third-party vendors, API systems that you're using. Change is constant, and most of that change happily doesn't matter, right? But understanding when those changes have impact on these kinds of external things is important. But we already have tools to measure that, right? So why aren't those tools working for us anymore? Well, this is another version of this question. What changed in how we work and the kinds of ways that we build software? And why has that led to a need for something like distributed tracing? If we can answer that, then we can understand how distributed tracing can improve reliability and performance. So the story I want to tell here is really in two parts. One, there's a series of technological changes, right? We've moved, many of us anyway, from bare metal to virtual machines to containers, and maybe even to things like orchestration tools like Kubernetes or serverless. And each of these has provided new abstractions for us, right? They've provided new primitives that we can use to build our systems, and maybe also introduced some new complexity in more ways for those systems to fail. But enabled by those new technologies, those new primitives, we've changed the architecture that we've used, right? We're starting to build things like microservices. And hopefully all these changes have not just let you scale your services more quickly, but your teams have been able to move more quickly and with a higher velocity. And speaking of teams, there's been a bunch of organizational changes as well. I mentioned DevOps earlier, and DevOps can really mean a lot of things, right? It can mean a collaborative environment where you practice things like blameless postmortems. For some people, it can mean a set of tools like CI/CD and things like GitOps. I think of it really as creating a feedback loop between developers and their users, a tight feedback loop where developers are able to get feedback from those users and integrate it into the kinds of features that they build, the tools that they use, and even the way that they work. And one of the ways that their work changes is, again, you have the same set of people that are responsible for both developing and operating systems. But one thing that's interesting, it's not often the case that it's just one giant happy team of DevOps engineers. It's often many teams that are all working independently, right? They're each choosing their own development processes, choosing what features to work on, choosing their own release schedules. And that's great, right? That they're able to work independently, because that means that they don't have to wait for each other, right? They don't have to coordinate as much, and they can all move more quickly. Now, when we think about the development lifecycle and overall, DevOps means that we can move thinking about performance and testing performance earlier in the process, right? We can move it back into a development mode. And that's great because that's more familiar for those developers. That's where they're used to working. And so if they can think about and measure and reason about performance there, that's great. And in fact, we might often need to move it earlier if we really want to take advantage of what DevOps can offer us, right? Because if we try to do it as part of QA, that'll require a single owner for that environment. And that's sort of contrary to this idea of these independent teams, and it's likely to become a bottleneck in your deployment pipeline. DevOps also means it's rare for a particular set of service versions to ever run together in the same environment before production. So I mean, like, version 1 of service A and version 2 of service B, those things might just never interact until we get to prod, right? Because we're not coordinating in the same way that we used to. And the other thing that's changed is that modern scale and architectures means that some performance testing has to happen in prod, right? Some kinds of user load just can't be reproduced outside of prod. And when you think about external dependencies, right, these, again, third-party APIs, those can't be replicated in a similar way. So, I've even seen some organizations get rid of QA entirely and just think about how to best do and think about performance testing at the ends of the spectrum. Okay, so for today, I'm going to go through a bunch of examples, and these are kind of three themes that are going to weave through all of those. So first is that understanding changes in performance is key to performance engineering, whether that's an on-call use case or not on-call. DevOps means understanding those changes throughout the software lifecycle. Again, thinking about moving from dev through other pre-prod environments if you have them, and finally into production. And despite the fact that these teams are going to be able to work independently and make their own choices about how to work and what features they're shipping and when to ship them, performance engineering and thinking about performance requires a global view, right? So it's not enough for each team to look at their own software and understand the performance that users are seeing. We really need to understand the whole system. And again, as I go through these examples, I'll try to call out each of these three things. So the plan for today, so I'm going to do a little bit of an introduction to and by a little bit, I mean a very brief introduction to distributed tracing, make sure we're kind of all on the same page there. And then I'm going to walk through these examples. And again, the idea is we're going to use this analysis of these traces to diagnose a bunch of different kinds of performance problems. Okay, so let's get everybody on the same page. Distributed tracing can mean a lot of different things. Of course, Lightstep as a distributed tracing tool, and so I'm biased, but I think I can say in an unbiased way that different tools provide different functionality. So it's not as though you're using a tool for use cases A, B, and C, and you can just go pick another tool and hit those same use cases. Like, they're going to provide different functionality. And people also think of distributed tracing as thinking about the data itself. So I want to talk a bit about that. Okay, so to start with some pictures. So, if you've used a distributed tracing tool, you might have seen something like this, or you might have seen a picture that looks like one of these. These are all different ways of visualizing individual traces, and they all kind of had the same Gantt chart-like feel to them, right? Again, you have time going from right to left. As you go from the top to the bottom, it's kind of going down deeper into your stack. And each of these colored bars represents the work that's done by some service as part of handling a request. And I'll say a bit more about this in a minute, but I'm going to say it a bunch of times. These traces are really just the building blocks of what you can do with distributed tracing. Okay, let me take and say some words. So there's a lot of kinds of tracing, right? You might think of like process tracing or kernel tracing, browser tracing, network tracing. These are all valuable things to do. When I say distributed tracing, I really mean tracing the path of a request across a distributed system, right? It's a way of gathering data about how those distributed systems are handling those requests. And traces are usually based on a form of telemetry called a span. And a span is a timed event describing the work done by a single service. So it has a beginning and an end. That's the timed part. And it describes the work in some way. So it's associated with the service, and it might have some other data as well. And I can hear one of my co-authors groaning a little bit when I say it's based upon spans. There are kinds of distributed tracing that are not based upon spans. The term span actually comes from a system built at Google. But for the most part, if you're using distributed tracing in industry today, it's probably based upon spans. So it's totally fine to think about it that way. So, and if that's the data, right, those are the traces. Tracing is a diagnostic tool that reveals how a set of services coordinate to handle those requests. And it'll go from a web app or a mobile app through your backends all the way through to your databases. And in addition to something like the service name and this timing structure, it'll also contain a bunch of other events, which you can think of a little bit like logs, and annotations, which are kind of like tags or labels. And in all of this, this is where my co-authors would definitely agree. Tracing provides a request-centric view of application performance. So in a lot of ways, I think of it taking sort of performance measurement and sort of turning it on its side, right? Maybe we usually think in terms of, per host or per process or per container data, instrumentation, or performance. And really what we want to do is turn it and think about per user performance. How is this user experiencing the application? And more importantly, how is that reflected by each of the different services that contributes to handling that request? So I said spans are an important part of this. There's a structure that's also pretty important too. So each of these bars represents one of these spans. Again, it has a beginning and an end. And as we go down the trace, these represent the calls from caller to callee. And as we come back up, these are the returns. And what that means is that traces encode the causal relationships between those callers and callees. And that means that you can know where responsibility begins and ends, right? Responsibility for performance or responsibility for failure. And while I've got this picture, I want to show one other concept, which is to just talk about the critical path. If you know what this is, then bear with me for a minute, but the critical path is like a really important part of analyzing and understanding distributed traces. And just like in project management, the critical path is sort of the long pole, right? It's the part of the process that's determining how long the overall process is going to take. So in this example, in this portion of the yellow span, the yellow service in the middle, that's kind of squiggled in here, it's waiting on the blue one to complete. And therefore we say that the blue span is on the critical path for this period of time. You can also think of it, it's kind of it's a leaf here, right? So that's what's making it part of the critical path. Another way of thinking of it is that you say that a span is on the critical path, or part of a span is on a critical path, if speeding up that span, if shortening its duration speeds up the overall request or shortens the duration of the overall request. Once you have that, now you can understand where to look in terms of how you think about performance. And you can do this not for just an individual trace, but you can do it for collections of traces as well. So for each of these different colored spans, each of these services, we can understand how much they contribute to the critical path here. And then we can just aggregate that across many traces so that we can build a model of how this is affecting performance overall, and not just of this one individual request. Now, if we do that, we can kind of compress the whole thing vertically, right? So now just kind of simplifying, we just have two services here, service A in yellow and service B in blue. And if we think about the contributions to the critical path across a set of traces, we can think about just rendering it kind of as these bars. And once we've done that, we can use Amdahl's law as a way of thinking about what matters in improving performance. Now, Amdahl's was originally used in the context of parallel computation, but it can also be applied to understanding performance in a distributed system. And what Amdahl's law basically says is when optimizing part of a process, you get the biggest benefit from optimizing the biggest part. And it also sets an upper bound on how much better you can make it. So of course, understanding the critical path is important, but understanding how much each service is contributing is also really important. So, in this case, if we just think about how this might play out, like if we were going to do some optimization work, we have a choice here, right? We could spend that time working on service A, or we could spend that working on service and optimizing service B. And what Amdahl's law tells us is that a 50% improvement in B is going to be better than a 50% improvement in A. Maybe kind of obvious. No improvement in A will ever improve overall performance by more than 15%, right? Because even if you reduced A to 0, that's not going to affect most of the time. And like I said, this is kind of obvious in a way, but it's only obvious once you have the data, right? So having that data is really important. But even I think for a lot of folks who are working kind of narrowly, heads down on their service, thinking about this bigger picture is not super obvious. And we actually saw this a number of times at Google. So when you think about a Google search, you type camera into that search box and you get a bunch of different kinds of results, right? You get web documents, you get news, you get images, you get products, you get video, you get personal results. Those different kinds of searches are all handled by services maintained and built by different teams. And so what happened at Google, maybe it still happens, but we had a MapReduce that would run each week that would look at the aggregate set of traces through web search, and it would look at all of the ones that we had. It would perform this analysis to see which services were contributing the most to the critical path. And that could then be used to then figure out who should actually go and do optimization work. Because before we had this analysis, teams would actually literally go off and spend weeks or months doing optimization work and maybe dramatically improve the performance of those systems, of their own services, but had absolutely no impact on the end user perceived performance because the services turned out not to be on the critical path. And so again, thinking about this, using traces to understand the critical path, build this sort of aggregate analysis can be really important in thinking about how to spend time and whether or not that should be time spent doing optimization or building new features or going on vacation or whatever. Okay, so to kind of wrap up this introduction, so to say it in a different way, traces are really the raw material. They're just the data, not the finished product. So when I say traces, I really mean just the data, the telemetry, which you can think of as just a bunch of structs, and not even very complicated structs for that matter. Tracing, though, is the art and science of deriving value from those traces. It's using those traces to make decisions about how to respond in the middle of an incident or how to think about optimization work over the next couple of weeks or months. If you want to know more, you can take a look at this paper. It was written by one of my co-founders and a bunch of other folks at Google. It describes Dapper, which is Google's internal tracing system. It talks about how they built it, how they deployed it, what it was used for, including this web search example. And while the paper was written now 10 years ago, it actually described work from even further back. This has actually informed a lot of open source tracing work that's been done since then. And if you're using one of these open source systems, this will actually give you a lot of insight into how things are working on the inside. And if you want even more information, I recommend picking up a copy of our book. Lightstep is actually making electronic copies of the book available for everyone. So we'll follow up with some information about how to get that if you're interested, but you can also pick up a physical copy wherever you find O'Reilly books. And really, this is something I put together with a couple of other folks, one of whom's at Twitter and the other at the Max Planck Institute for Software. And so it describes not just, it's not Lightstep specific in any way. It actually takes a very broad view of distributed tracing, how to get started and thinking about instrumenting your application, how to deploy a tracing solution, whether that's something from a vendor or an open source solution, and how to think about the trade-offs and costs there. And then a bunch of examples about how to use distributed tracing and even what distributed tracing might look like in the future. Anyway, we'll follow up with more information about that, but check it out if you're interested. Okay, so I want to go and talk about some real world examples now, and I'm going to show a bunch of Lightstep screenshots in this, and that's not because I'm trying to pitch you on Lightstep. I'm really trying to pitch you on this kind of analysis of distributed traces and thinking about distributed tracing as this kind of set of analyses. But I wanted to make the examples real, and the real examples I have today are actually from operating Lightstep itself. So these all come from what we call our meta environment. So this is Lightstep monitoring itself to see a bunch of keywords about trace analysis and stuff like that, just remember you got to wear your meta hat. You're someone who's thinking about operating Lightstep itself. And some of these come from pre-prod environments. Some of them come from our prod environment. I'm not going to say which are which. Okay, to start simple, this is a trace that I actually just found while I was looking for something else. And as someone who's looked at these things for a long time, there's an opportunity for optimization that I saw here, which is actually pretty straightforward. So this is part of our trace analyzer component. And it's basically taking a bunch of traces, dividing them into 3 batches, and then fanning out that work across 3 instances. And what you see here is that those 3 instances are actually take very different amounts of time to process that, right? So one of them takes about 600 milliseconds and one about 200 milliseconds, and the other one almost 2 seconds. If we were to rebalance that work, we actually could improve the overall latency of this request by almost 50%. And that's without, even opening up a CPU profiler or anything like that, right? That's just making sure that the work is balanced among these different pieces. And, it's possible to see this maybe through thinking about looking at different kinds of metrics. But there might be some of these requests that just naturally take longer than others. That's fine. It's really understanding within a specific request, what's the fan out, what's the balance among the different pieces of the fan out, and what's the variation among the time that those things take to process. And understanding that is much easier using tracing. Another quick example to continue our kind of warm up here. This is a portion of a very large trace. And if I zoomed out, you could kind of see that there's a slow progression of these SQL requests, kind of sort of from left to right here. And when we built this software, originally, it was fine to make a few of these requests, and something changed, right? Maybe user behavior changed. Maybe we actually recommended that users change their behavior in some way. But what that led to is many, many, many of these calls being done in sequence. And when in fact, we can actually just do one SQL call, which, itself will take a bit longer, but overall the request will go much, much faster. So that's kind of easy optimization to see with this sort of distributed tracing. Okay, now I want to really dive in. So this is actually, I think this one might have come from one of our operational reviews, but we were debugging some latency, which we didn't know had to do with queues, but that's what we discovered. It started with an engineer trying to look at one of our services called Maggie. That's our metrics aggregator. And they had just done a deployment, and so we're kind of keeping an eye on a dashboard to see what was going on, and they noticed this jump in performance here, right? So this is a latency graph where we're showing 3 different percentiles. The blue line, which is basically flat, is the P50 percentile. And then we've got 2 higher percentile latencies above that. So these are showing not necessarily outliers, but what is the performance as seen by the users who are seeing the worst performance. And you can see that there's a big jump in these high percentile latencies, especially the green one. And the engineer who was looking at this wanted to understand what's happening. So what they did is that they took a collection of traces from the period where the regression occurred, right? So there was about 1,000 traces that happened during this period around noon, which is colored in yellow. And they compared that to about 1,000 traces that had happened a few hours earlier, right? When things looked better. What they did is they took those 2 collections of traces and they plotted the latency on a histogram. It looked something like this. So the baseline, that's the one from a few hours ago, that's plotted as a blue line here. And then the yellow bars represent the latency as during the regression. And this is a histogram, right? So along the horizontal axis, we're actually showing the latency or the span duration. And then the vertical axis is the frequency. It's how many times each of those different latencies occurred, right? So in this case, you can see that really fast ones, there's about 10 million examples in this larger collection. And then as we look further out, this is plotted on a log scale. So you can see sort of there's a couple of different bumps in terms of the behavior, but overall, there's been a shift in the behavior where everything got a bit slower, right? Or at least it looks like everything got a bit slower, but that's what we're trying to figure out here. So let's dig a bit deeper and see what's happening. One thing is we can look not just at the sort of top level latency, but we can look at different pieces of what's happening within those traces. And one thing is that we can look at tags or annotations within the spans throughout those traces. And one thing that we discovered in this case is that that the latency is associated with a particular topic. So this is pulling data from a Kafka queue. And when we pull data, we annotate those part of the processing with a tag called topic. And in this case, the average latency of spans that had to do with the public lightweight aggregate topic went from about 300 milliseconds in the baseline to about 560 milliseconds in the regression set. So almost a doubling, not quite. And that's the latency of the spans that have that particular tag. So now we've already gone from just thinking about, there's a latency problem all the way to thinking about particular Kafka topics. Particular Kafka topics. If we want to dig in, try to find out, what's happening a bit further, we can look at a picture and say, like, well, what are the operations that are actually present in here, right? And we can see that this is actually the latency here, as represented by this kind of orange yellowish halo, has to do with this third-party library that we're using to actually interface between our Go application and Kafka, and that now we can see that it's really sending messages into this Kafka queue where things are slowing down. And if we want to dig even further, we can actually validate that it is really this particular topic, right? So now we can highlight those traces that are associated with this topic. And those are the ones here that are actually highlighted in the darker yellow in the graph. And those are ones that actually shifted out, right? So it's not as though in this case that all operations got slower, it's just ones associated with this particular topic. So now we can try to understand maybe that topic needs to be configured in a different way, or maybe we need to change the way that we're actually, the messages themselves that are going on that topic. Okay, let me take another example. This time, again, we didn't know what to start out with, but we're going to end up thinking about resource contention. But we started from the same signal, again, thinking about latency, and this time in a different service called Aggie instead of Maggie. Again, we're trying to understand what changed here. So we see this bump, and we're going to do a comparison by looking at a bunch of hundreds or 1,000 traces to try and find patterns. We're going to look at a set from around when the regression occurred and compare that to what was happening earlier. When we do that, we can actually see one of the tags that pops out here is that has something to do with the trace assembly process, and that's actually gone up in a big way. But what's interesting in this case is that like I said, the latency was actually measured first in a service called Aggie, but the contention is actually happening several services away in another service we call a trace assembler, and it has something to do with this write lock acquire operation. And what's interesting is that that's many steps away from where the actual problem was seen originally. But tracing is able to surface this for us very quickly and help us understand what's happening. We can actually even dig further, and we can group within that service down at the bottom of the stack, try to understand more about what's happening, because we saw that this particular tag was showing up and telling us something about what was happening when we were grabbing this lock. And if we group by the values of that, this actually tells us something about Lightstep's customers and how they're using it, because this particular project 285, was actually seeing the bulk of this latency increase. So it wasn't an overall problem. This wasn't something where we had deployed new software and we saw a problem. This was actually a customer that was using and had changed the way that they were using the software in a way that was forcing or that was creating contention for this lock, and helped us to think about how to re-architect that particular component to handle this kind of new load that we were seeing. Again, not something that changed in terms of a software release, and not even something that was, again, we saw the latency in terms of how Aggie was behaving, but we had to look much deeper to understand where we could actually fix it. A quick side note, I talked a little bit about histograms. This doesn't have anything to do with tracing, but histograms are great. This was a histogram that we were looking at when we had just deployed a new version of one of our services, and that new version had a cache in it. So we were thinking about how to improve performance in this case. And when we did that, we were hoping to see an improvement in performance. But when we looked originally just at P95 latency, it didn't change that much, which in some ways is maybe expected. But what did change is that the older behavior, again in this red line here, and the new behavior in the blue, is that we saw this whole new mode, right? A whole new kind of type of behavior in terms of the performance, where a big chunk of that had actually just moved over to the left, where it was much faster than it was before. So again, hard to see if you're just thinking about individual metrics, but really thinking about the shapes of these distributions is pretty important. Okay, I want to talk about one last example here, and that's really not about latency this time, but about a spike in errors in a service that we call Crouton for reasons. And if you look at this red graph here, we had this spike in errors. And, if you look carefully, it's not a huge percentage of errors. It's just the rate of errors jumps to about 0.3%, but still something that we want to get a handle of in case it's something that's going to occur more frequently in the future. So again, we do the same thing as we did with the latency example. We're going to take two sets of traces, one from when the errors were occurring and one from before that, and then we're going to compare those two things. And in the previous examples, I was talking about how to use tags or other annotations to kind of understand discretely, like, is there something fundamentally different about these requests that changed? In this case, we're actually going to go look at the logs instead. And what the tracing tool, what Lightstep in this case is able to show is not just that there's logs that matter, but logs actually in a different service. So remember I said that the errors were actually first visible in a service called Crouton, but what the tool is showing us here are actually logs from a service called LiveView, which is deeper down in the stack. And this particular log message, which is talking about some bad base64 encoding, never occurred in the baseline set, but occurred 54 times in the regression set. So that's a pretty strong signal that this might have something to do with those errors. And, in fact, we can actually dig deeper and go look eventually at a trace if we want to understand what's happening there and see where the error message occurs. And we can go use this to go back up the stack, not only to Crouton, but further up to the stack if we actually want to build some sort of steps to reproduce this thing back from the API layer itself. So again, this is a case where, I didn't have to grep in through Crouton's logs. I didn't even have to, try to think about what other services could be affecting this. The tracing tool can actually tell me directly which services are affected and which data from those services can help explain what's going on. Okay, this might all sound great to you, but you're thinking, well, this has got to cost a lot, or maybe this is going to slow things down, right? I'm talking about thousands of traces all the time. What we found at Google is actually that's not the case. And the way that Google handled this and the way that many other solutions do is to do some form of sampling. And, I often hear folks being concerned about that on my application. As far as I understand, it's still true today. This was true at the time when I was at Google, that the tracing instrumentation was always on. So that code is always running in production at Google for every request that comes through. But in order to manage the network and storage costs associated with that data, that we had to do a form of sampling. So essentially, there's a coin flipped at the beginning of every request, and 99.9 or 99%, 9.99% of the time, we just don't emit any trace data. And for a small set of requests, we do emit that trace data. And in either case, we actually have to propagate that decision down the stack so that that decision is being made in a coordinated way. But like I said, the idea of keeping all the data, it became untenable from a network and storage cost far, far before it actually became an issue in terms of application performance. And like I said, Google did this in a totally uniform way. That was partly because Google's requests are pretty uniform, as it turns out, in the sense that the surface of Google is pretty simple and not that complicated. But it also turns out the kinds of analysis that were important at Google were actually unhindered by this kind of uniform sampling. But sampling can actually be, sampling decisions can be made for in a lot of different ways. And so when you're thinking about a distributed tracing solution, you should ask what kinds of sampling decisions are being made, because in order to manage costs, there are definitely going to be some form of sampling decisions. And you should ask what information is being used to make those decisions and when is that information being used. And the way that you answer these questions is, again, thinking back to your use cases, right? Are you interested in, overall aggregate performance of something like web search over the last week? Or, maybe you're interested in debugging, a canary release and understanding that, or like the examples I gave today, digging into particular performance problems or understanding errors. There's a couple of cases that I'm going to talk about in the next few slides where we can actually drive sampling decisions from outside the application as well, right? So I want to talk about some integrations that we can use to do that. The first one is through a CI/CD integration, and there's a bunch of ways that we can do that. So one is that we can collect traces on every build failure. So again, this is using information from outside the application to inform when we want to keep tracing data. And if we do that, we can link from those failed builds back to that tracing analysis and help us understand what's there. We actually can collect traces on every build as well, maybe not every request, but on many requests. And we can actually use that analysis to inform a go or no-go decision on the continued deployment of a particular service version. We can also link from traces back to deployments, right? Once we've deployed to prod, linking from the trace is something that we've done at Lightstep and others have done as well, where you can then quickly, once you've found the problem, whether it was in the first service that you started investigating or something deeper down the stack, to link back to the deployment tool so that you can easily roll that back. And then finally, using the version annotations from your CI/CD pipeline can actually be important in distinguishing those different deployments. And that's especially important when you have incremental deployments like a canary or blue-green, because there's not a discrete point in time where you switch between all requests being handled by one service version and by a next one. There'll be a blend of those two things. And so having some sort of annotations can help do a better job of that kind of tracing analysis. The other kind of integration that I want to talk briefly about was thinking about alerts, right? So we actually have integrated Lightstep into our incident management tool, into PagerDuty for us, so that when an on-call engineer gets a page, they actually get a link from that directly into the tracing tool, right? So that means that there's evidence here, right? This is a page where one of our services is behaving too slowly, and here's an example, evidence of it being too slow, right? So we can immediately start digging in and understanding what's happening there, and starting to understand and build those comparisons. You can actually go in the other direction as well, right? So this is an example where we sort of linked from an alerting tool into tracing. We can actually use tracing to drive alerting as well. That is, you're actually using tracing to determine where alerts are delivered, like which team is going to get paged. And I'm not going to say too much about that, except for to plug a talk that I'm moderating in a week or so. That's Are We All on the Same Page? Let's Fix That by Luis Minero. He's going to talk about how they use tracing to actually change the way that those traces were routed. And it's pretty cool. So if you want to hear more about that, check out 99%devops.com. Okay, so to kind of sum up a little bit here, we looked at how changes in performance can simplify analysis. That's both for humans and algorithms, right? Then when you can compare two sets, you can draw much stronger conclusions about what kinds of changes are actually important. I talked about using signals throughout the life cycle, from prod all the way back into dev, to understand what's happening. That can be changes in SLIs like latency, but it can also be changes in the distributions themselves, right? In the shape of those distributions. And I talked about integrating with other systems, whether it's something like CI/CD or alerting systems. And in all these cases, tracing is used to provide context, right? It's what allows us to make good decisions about where to continue our investigation. And using an automated analysis can actually kickstart a lot of that investigation for us. Before I go, I wanted to let everyone know, if you want to learn more about Lightstep in particular, you can go to this address, go.lightstep.com/requestademo to learn more. And yeah, with that, I'm happy to take questions from folks. But thanks for your attention so far. Again, if you have any questions, there's I think it's down here in the bottom somewhere, a little QA button that you can click on and type them in there. Maybe while people are typing, I can think of some questions that come up a lot. One thing that folks ask a lot about is, how does distributed tracing compare with logs and metrics? These are kind of sometimes touted as the 3 pillars of observability. And there is a relationship. In some ways, I actually like to think of them as 3 kinds of data, right? So we have metrics as a kind of data where we've aggregated in one particular way, right? We've turned the very raw events into something like a counter or a gauge. Logs, on the other hand, we've not done that kind of aggregation, right? And traces are a form of telemetry where we have these connections between different parts of the application, and they're all important in their own ways. The thing I think that's really valuable about tracing is that it actually can be used to drive both the collection and analysis of those other pieces, right? So to me, 3 kinds of data, yes, but thinking of logs, metrics, and tracing as 3 separate tools actually misses a lot of opportunity, both in terms of, again, how we analyze that data and doing that in a cost-effective way. And like in some of the examples I've showed, where we actually use tracing to find the right logs to show developers the kinds of questions that they might need to be thinking about, and maybe even some of the answers to those questions. Okay, I don't see any questions. Well, I guess we'll wrap it up then. I want to thank everyone for your attention. I'm glad that you joined today. If you have other questions, you can find me on Twitter at save_spoons. We'll follow up with an email, like I mentioned, where we'll have a recording to this talk and a way to download a copy of the distributed tracing book as well. So with that, thanks again, and I hope everyone has a great day.